Okay, for this video, we are going to focus on exothermic reactions, and we're specifically going to be looking at energy diagrams. So the first thing we need to do is recap what we've already learned. We've already learned about Q, and we know that Q equals m shot, so the mass times the specific heat times the change in temperature that has occurred. So the Q is actually telling us how much heat is transferred within the system. So now we're going to start looking at chemical reactions as either being exothermic or endothermic. And like I said, we're going to focus on exothermic just for this video. So what we're going to see is we're going to see something called delta H. Delta H is basically equal to Q if we are at a constant pressure. Now, because we are doing these reactions in the classroom, we're always just going to say that the amount of potential energy in the system, so delta H, is going to be your thermodynamic potential of the system. So how much potential energy, how much potential heat can be transferred. So we've learned Q equals mass times specific heat times the change in temperature, which is the heat transferred. So delta H is how much potential heat transferred, how much potential energy is there. One other word that we are going to be seeing is enthalpy. And that's just another way of saying delta H. That's how much potential energy a system can have. So whenever you read enthalpy or see that, they're just talking about how much potential energy the system has, which for us is also going to be the same as Q, mass times specific heat times delta T. Okay, I'm only going to talk about exothermic reactions. So when we think of the word exothermic, you should be thinking of exiting. So energy is exiting the system. Energy is being released from the overall system. Okay, so exo, exit. Now, what that means is that you're going to feel warmth coming from the reaction. And that's because that energy is being released from the system. So if I have material going in, which are the reactants, that is what goes in. That's going to have less energy or more energy than the products do. So let's say that we start with material that has 300 joules of energy for it. But then we find that our products only have 200 joules of energy. Well, where did this energy go? That means that 100 joules of energy was released. So here, energy is released. And what happens then is that that heat is flowing out of the system, and so it feels warm to our touch. Okay, so in an exothermic reaction, the system loses heat, okay, the heat flows out of the system, and delta H is then negative. Now, remember delta H is going to be negative. Delta H is the same as Q. It's the same as Q. So how do you end up with a negative Q? Well, Q is equal to mass times specific heat times delta T. Well, can we have a negative mass to get a negative number? No, you can't have a negative mass. It has to be a full number. Can we have a negative specific heat? No, we can't have a negative specific heat. So that means our delta T must be negative in order to get a negative Q. Well, how would we get a negative change in temperature? Well, let's think about this. Our change in temperature, delta T, is calculated by taking our initial temperature minus the ending temperature. So remember, exothermic feels warm. So let's say that our starting temperature is 100 degrees Celsius And our ending temperature is 125 degrees Celsius. Well, 100 minus 125 gives us a negative 25 degrees Celsius. So there's your negative number. Exothermic energy is exiting the system, which means that our change in temperature is what ends up giving us that negative delta H right there. Okay, so heat flows out, we get warm. Our delta T right here is a negative number, and then that ends up providing us with a negative Q, which means delta H is negative. Okay, so with exothermic reactions, energy is going to be a product of that reaction. So let me give you an example. Let's say that we are doing a chemical reaction of maybe a heat pack. Okay, in a heat pack, we have typically what there is there's iron, and when that iron comes in contact with oxygen, it produces the compound of iron oxide. Now we have to balance the reaction, so I'm going to put a 2 there, I'm going to put a 4 there, and a 3 there. Well, when this reaction happens, heat is a product. So we would say that delta H is equal to negative 1,625 joules. So that means that 1,625 joules was given off. So if I were to show this in a graph, I would start with my reactants having a higher potential energy. So I would put my reactants up here. Now, energy is going to be given off, so that means that the products are going to have less energy than what the reactants started with. So let's say that the products then, my iron oxide, is down here with less energy. Well, where did this energy go? Well, this energy was a product. It was released. So that means that 1,625 joules of energy was released. And so because of it being released, it's exothermic. It gives off a delta H that is negative. So if we were to actually write this whole chemical reaction here with energy, we would actually write it as 4 iron plus 3 oxygen molecules yields 2 iron oxide plus 1,625 joules of energy. And this is part of your product then. So like I just said, in an exothermic reaction, the energy is going to be a product. So you can see here, our reactants are going to start higher up than our products. Well, in order to get any sort of chemical reaction to occur, we actually have to add energy into the reaction. And so this addition of energy here, any energy added, is going to be called the activation energy. So on this side it says energy added to make the reaction occur is called activation energy. So as we said at the beginning, an exothermic reaction is going to have this energy as a product, okay? We are going to have, let's say that our reactants here start with 200 joules of energy. We have to add energy to get the reaction to occur, but then there's less energy available. Now this energy right here is called activation energy. The difference between the reactants and our products down here, let's say this is 100 joules, that means the difference between these two is going to be your delta H. So your delta H is going to be the energy of the products minus the energy of the reactants. So 100 minus 200 gives me a negative 200 joules of energy. So it's negative exothermic energy was given off. So the minimum amount of energy, like I mentioned, is called the activation energy. So that's how much energy is needed right here in order for the reaction to occur. So this, from where the reactants start to the high point here, this is called the activation energy. If you were writing an equation, let's say that I'm starting with my reactants of hydrogen gas and oxygen gas, and then that creates 2 molecules of water. Let's say this is an exothermic reaction. That might not necessarily be, but let's say that our delta H is equal to negative 572 kilojoules of energy. If we were to take this energy and actually write it into the chemical equation, we would say that H2 plus O2, and of course we would balance it, so we would need to put a 2 in front here, is going to yield 2 molecules of water and 572 kilojoules of energy is being given off. So that's how we would actually put energy into the chemical reaction. It is a product in an exothermic reaction. So this heat is being given off. So it feels warm, and again, that delta H is negative because it is a product. So I don't want you to be confused. Our activation energy is how much energy it takes here to make the reaction occur. That does not affect our delta H. So our delta H is going to be determined by taking the energy of the products and subtracting the energy of the reactants. And so that's how we end up with that negative delta H. Just like in that other example, let's say that our water and our hydrogen and our oxygen started with 1,000 joules of energy, and then at the end there was 430 joules of energy. Well, if we take 430 and we minus 1,000, we get a negative delta H, and so the energy was given off and it was an exothermic reaction, and so that's negative H is exothermic. So chemical reactions require energy in order to make them happen. That's called our activation energy right here. The activation energy doesn't affect our delta H. Okay, it just is how much energy is needed in order for the reaction to go on. We can actually lower our activation energy, and we do that with what is called a catalyst. So we can speed up chemical reactions by adding a catalyst, and so now instead of the chemical reaction taking the red line in energy, it only takes the blue line. But it still ends at the same location. And so you can see how my delta H would not be affected at all, because delta H is always the energy of the products minus the energy of the reactants. And so you can see my reactants didn't move. The energy of my products doesn't move. It's simply just how much energy has to go into the reaction right here. So a catalyst does not change your delta H. All it does is change how much energy goes in to the reaction in order to make it move forward.